Hello and welcome. My name is Gergely Molnar, and in this short tutorial I am going to show you how to simulate nano-indentation on amorphous silica. We are going to use two different yield criteria. First, an empirical one, which was published by Guillaume Kermouche in 2008, and then another yield criterion, which is inspired by atomic scale simulations, and what we have published in 2017. I am going to use an equivalent geometry for the Berkovich indentation, which is an axis symmetric geometry, and we will compare the results of the two different yield criteria. Now, let's get started. After opening the graphical user interface of Abaqus, create a standard explicit model. Make sure that your work directory is set correctly. Then save the model. Let's name it Indent. Let's rename our model and call it Kermouche 2008 and start creating our parts. We will make both the indenter and the substrate in one part. This should be an axis symmetric part. Let's name it sample. The approximate size is going to be 0.1. Click continue. First, we will create the approximate geometry of the indenter. We would like to indent the substrate with 2 micrometers, so the overall height of the indenter is going to be 10 micrometers. We are going to do everything in millimeters and newtons, and this way we are going to use megapascals. Don't worry, we are going to do only an approximate shape of the indenter, and then we are going to set all the parameters precisely. Let's finish the polyline, and now we can set this height. It's going to remain 10 micrometers, and then set this angle, which is going to be 70.3. This will modify the height of the right side. Now we will move the whole geometry a little bit upwards to create a very small gap in between the substrate and the indenter. Now we can start creating the substrate. Pay attention that the y-axis here is going to be the axis symmetric axis, where we will rotate our whole model. And this is a negative. And let's click done. Don't forget to save your model. Now we are going to divide this part into 2 subsections in order to simplify the mesh procedure. We will do this by creating additional lines. The first one is going to be approximately here. We will set that this line remains horizontal. Then we can precisely define its position. Then we can create other guidelines to help our meshing procedure. We can set this distance to be constant. This will remain what it is. We can delete then this line here and set an equal length between these two lines. Additionally, we can add another guideline, but it doesn't really matter what is the exact dimension. Let's save and move on to the next module. In the property module, we will create two different materials. One is going to be diamond, which is going to be our indenter. This will be elastic with a Young modulus of 1,000,000 megapascals. One too much zero, and with a Poisson ratio of 0.07. Let's click OK and create a second material, which is going to be silica according to the Karamush model. Here we will add solution dependent variables. As we are in an axis-symmetric simulation, we will have 4 stresses and 4 strains. So 2 times 4 is 8, and plus 1 is the equivalent plastic strain. So we will add 9 solution-dependent variables and a user's material. Let's look at the UMAT file, what kind of material properties we need to add here. First, we will add the Young's modulus, then the Poisson's ratio, then a yield stress, which is going to be a von Mises stress, a deviatory stress at 0 pressure, some kind of initial pressure value in a hydrostatic stress. Thus, this is going to be a negative stress value, where the pressure starts to yield and to densify, and then a hardening coefficient. If we go back to the original paper, we try to find the hardening criteria defined by the authors. We will see that the first value when the pressure is going to be yielding is around 11.5 gigapascals, and it will harden constantly with a 100 gigapascal hardening coefficient. Let's go back to our abacus simulation. So we will add 72,000 for the Young modulus in megapascals, 0.18 for the Poisson's ratio, and then 6,500 for the von Mises yield, minus 11,500 for the initial yield pressure, and 100,000 for the hardening coefficient. By clicking OK, we accept all what we added. Now we will create 2 sections. One is going to be the indenter section, which will have a material of the diamond. The second one will be the substrate, which is going to be silica. Then, creating 2 sets, we are going to assign these properties to our part. This is going to be the substrate set with the substrate section, and this is going to be the indenter set with the indenter section. We can close this window we can save our model and step to the next module. The next module is going to be the assembly module. Here we simply create an instance, we click OK, and we define our sets. In the assembly, find the set menu. By double clicking on it, we will create a few sets. For example, the bottom set. Continue, highlight the bottom edge, click done. Next, the right, highlight the right side, left. Here pay attention to select all the edges which is on the left side, click done. Create the top, continue the top edge, click OK, and here we have to create a reference point which is going to be measured from this point. We will add 1 times power minus 10 power minus 3 equals reference point. And creating the reference point, we will use this reference point to actually measure the reaction forces which are on the indenter. This is going to be a reaction point. Continue and select the reference point. Click done. Don't forget to save your model after everything we have done in the module section. In this step, we will create a new simulation step, which is going to be a static general step. The increment is going to be set to 100 of an increment, and to have enough output data, we will put 0.01 to the maximum value as well, and we will increase the maximum number to be able to simulate this. And we will switch on nonlinear geometries as we expect 10–20% strains. By clicking OK, we accept what we have done. Now we will modify the requested field outputs. We do not need anything else, just the displacements, the reaction forces, the logarithmic strains, the stresses, and the solution dependent variables. OK, dismiss, and again save your model. Go to interactions. Here we have to do two things. First, define the contact between these two edges, and then create an equation, a constraint between the reference point and the top surface. First, we will create the equation, click continue, set 1 and -1 for the coefficients. The set name is going to be the top, as we are going to couple the top edge to the reaction point, and the degree of freedom is going to be the second degree of freedom, which we will couple. By clicking OK, we will see that these two sets are now connected. Let's create an interaction between the two edges. Create a tangential behavior, which is now going to be a frictionless behavior, and the hard contact normal behavior. Click OK, and let's assign this to these edges. We will create a surface-to-surface contact. The master surface is always going to be the harder material. Let's click done. The other one is going to be a surface here. Let's select the substrate and finish this definition. Make sure that your contact interaction property is selected, and click OK. Save the model. And that's it for the interaction module. Let's go to the next, which is going to be the module where we set the boundary conditions. here we will create boundary conditions on the bottom. Let's select a set as a boundary condition, where we will constrain the translational degree of freedom in the y direction. On the left side, we will create a boundary condition which constrains the displacement in the first, so the x direction. We will do the same on the right side, continue right in the x direction again, and we will apply a load on the reaction point. This load is going to be added in the y direction. However, we are going to use a table, an amplitude. At 0 time, we are going to have a 0 amplitude. At the middle, we are going to apply 2 micrometers. And when we go back to 1, the indenter will return to its original position. Click OK and make sure that you select your table. Make sure that this number is -1, so we are going to indent the substrate. Click OK and save the model. Let's go to the mesh module. Make sure that you will mesh your part. Let's zoom on to the indenter. Let's create an initial seed, which is going to be a 0.002 size mesh. Let's remesh our edges. For the indenter, select the predefined edges, click done, and set a 0.0002 millimeter mesh size. This is going to be dense enough for our simulation, at least for the tutorial. Then you can do the same for the inner part of the substrate. Good. To create a transition between the coarse mesh and the finer mesh, we will add a simple transition where this is going to be a single variable transition between our small mesh and the larger one. Click OK. Yes, we need to turn. No, we need to turn the other one. Sorry. Let's flip it. Click OK. So the outer side is going to be mesh like this. We have one other important thing to do. The UMET doesn't like reduced integration points, so we will use bilinear axis symmetric elements like this to have a nice mesh. We won't use the mapping procedure, and then let's mesh our model. This looks quite nice for the sake of the tutorial. Let's save and go to job. Now we will do two things. We will duplicate this model and name it Monarch 2017. In this model, we are going to change the material property of the silica. So we'll create a new silica. Where we will add the same kind of solution dependent variable, however, to 4 elastic strains and 4 plastic strains, we are going to add 3 equivalent strains which are used by the UMAT itself. This is going to be 11, and add a user's material. Let's look at the UMAT file, what kind of properties which we need to add. First, the Young modulus, the Poisson's ratio, the parameters of the yield function for the Prager-Drucker shape, the extended Prager-Drucker shape, then parameters for the hardening of the positive pressure value and the negative hydrostatic stress value. This is going to be sigmoidal hardening according to Caravan's work. And then an interaction parameter which defines at which part of the pressure axis the cap is going to be active. So differently from the model of Guillaume-Kermouche, in this model we're going to use a sigmoidal function defined by Caravan in 2014, which looks exactly like this and uses the material properties defined in this paper. Let's go back. So first we will add 72,000 for the Young's modulus, 0.18 for the Poisson's ratio. Here we have 3 parameters which define the shape of the yield function. For silica we found a relatively large exponent for the Prager-Drucker shape, which we will see that confirms the original empirical model of Guillaume-Kermouche. So the exponent is 5. The yield stress, the yield strength at zero pressure is 5,700 megapascals, and the positive hydrostatic, the tensile hydrostatic stress value where the material yields is 5,000. Now we will add a negative value, which is the first yield pressure, the maximum relative volume change, which can be related to densification. So this is going to be a negative value, so we lose volume. Then shape parameters defined by Caravan, the middle point of the sigmoidal function, and the delta P parameter, which is going to be the part where the cap, the positive part, is active. By clicking OK, we accept this. Let's dismiss this window and change the section, the material for the substrate section. Click OK and dismiss for the model of Monar 2017. In the job section, we will create 2 jobs. One is based on the Kermouche model, where we will add the subroutine like this. Click OK, and then we will create another one based on the atomic scale simulations. Continue general subroutine, and the other one. Okay. We can launch both of these jobs and wait for the results. After both simulations are completed, we can look at the results. First, go to the model of Guillaume-Kermouche. Let's create a field output. let's look at the result of unique models. We will see the reaction force as a function of the top displacement element set, node set, and the reaction. Let's plot it. Let's work on the XY data. Let's combine the two displacement and reaction forces. Let's plot the expression and click cancel. We will see that the maximum reaction force is around 450 millinewtons. Let's look at the other model. We will do the same. Unit models, second translational degree of freedom, the same reaction force, node set, reaction point, plot, and as we saw, this is quite similar, as both models were calibrated originally to reproduce the reaction forces, the same maximum reaction force at 2 microns. However, if we look at the densification map after indentation, so the 9th solution dependent variable, we will see that in the case when we used the material model based on atomic scale simulations, the maximum volume change is around 10%. However, if we go to the model, the empirical model, and we look at the same, it increases to 16–17%. To conclude, in this tutorial we saw how to model nano-indentation, so the plastic deformation of amorphous silica with an equivalent geometry. We compared two different yield criteria, one empirical, when the cap itself stays in place, however the maximum pressure value increases, or another one which was inspired by atomic scale simulations, when the cap moves, so less densification can appear. If you have any questions, please do not hesitate to contact me. I will be happy to answer all the questions. Thank you very much for watching. See you next time.